Next up, we're going to look at something called conditional probability. Now, I have a note down here at the bottom. It says often we can find conditional probabilities directly without need for the formula. It's easier to understand this formula in terms of conditional probability, but if you multiply both sides by the probability of A, you get a formula for the probability of A and B. So it's going to be the way that we eventually get to a formula for the probability of A and B. But we do have a formula for the conditional probability, but I'll show you a lot of times you can compute it directly by restricting the sample space is basically what you're doing. So the probability that one event happens given that another event is already known to have happened, so we have more information which reduces the size of the sample space. Okay? That's called a conditional probability. Okay? So when the probability of A is greater than 0, then, because if the probability of A was 0, you divide by that, it's undefined. But when the probability of A is greater than 0, the probability that event B happens given that event A has happened is found by, and we have a symbol for this. We use this vertical bar, and you read that as given that. This is the probability of B given A, okay, or the probability that B occurs given that we know A occurs. So the way I think of it is, in general, you would have the number of ways that the success occurs divided by the total sample space. And we can do that in terms of probabilities as well, and the common denominators would cancel out. So if we think in terms of counting, if we're given that A occurs and we want B to occur, A and B both have to occur. So a success is going to be when A and B both occur. So we've got the probability that they both occur. And our sample space, normally you'd divide by the size of the sample space, but we know A occurs, which has shrunk our sample space. So now it's just all of the ways that A can occur. So the common denominators would cancel in terms of the probabilities if you looked at the strict formula here and tried to prove this thing. But just conceptually, if you look at the number of ways B can occur given that A has occurred, your successes would be when A and B both occur, and the total sample space would now just be when A occurs. So there's our formula for the conditional probability. So the probability of B given A, is how we read that, is equal to the probability of the intersection, A and B, divided by the probability of A. Okay? And A and B, of course, are just labels. We could write a formula, the probability of A given B would be the probability of A and B divided by the probability of B. Okay? Whichever one is given, that's the one that's going to go in the denominator. Okay, so an example to show that the formula makes sense. If I randomly select a card from a standard deck, the probability that it is a queen given that it's red, okay, you can compute that directly. If we're given that it's red, you've cut the deck in half and there's only 26 cards and 2 of them are queens. You have the 2 black queens, they're gone, all the black cards are gone. If we know the card is red, then there's a 2 out of 26 chance that it's a queen. So I can compute that. That's a conditional probability. I can compute it directly without using the formula. I just think about the sample space. But if we did use the formula, basically we'd have a common denominator that cancels out. So it would be the probability that it's a queen and red divided by the probability that it's red. So the probability that it's a queen and red, well, there's, out of the entire deck, there's 2 cards that are queens and red. There's the hearts and the diamonds. So you have a 2 out of 52 chance of getting a card that's a queen and red. The probability that's red is 1/2, or 26 out of 52. The 52s will cancel and you get 2 out of 26. Okay. So the formula works in that case, but it's overkill. It's easier to just think about the deck. If it's given that it's red, there's only 26 cards left and 2 of them are queens. But the formula does work, and as we see, well, I'm going to do an example with a table. Let me skip ahead for a second to make a point here. Let me stop the animation. I can't with this one without redoing the whole video, which I don't want to do. So let's do this example first, but then I'll show you we get formulas for the probability of A and B that are useful. So example 3, we're not going to need the formulas at all here. We're just going to count things in the table, but we are going to do a conditional probability on part C. So suppose the following table summarizes the number of on-time and delayed flights for 2 airlines. What is the probability that a flight selected at random from this group is delayed and made by Alaska Airlines, is delayed given that it is made by Alaska Airlines, which is a difference. There's a big difference between B and C there. Okay. But on part A, what's the probability it's delayed? Okay, so that's out of all the possible flights. We haven't restricted anything. So it's the number of delayed flights out of the total number of flights. And we're going to have to do some addition across the table here, right? So there's 2 different airlines. You have the number that's on time for Alaska, the number that are delayed for Alaska Airlines, the number that are on time for America West, the number that are delayed. So there's 501 that are delayed for Alaska Airlines, 787 that are delayed for America West. I add those together, I'll have the total number that are delayed. And if I add all four numbers across the bottom up, that would be the on time and delayed for Alaska, on time delayed for America West, I would have the total number of airlines. So my probability that's delayed would be 501 plus 787, that's the number that were delayed, divided by the sum of the four numbers on the bottom, which would give me the grand total that there were 11,000 flights. So we wind up with 1,288 out of 11,000. And when you have numbers that big, we usually prefer a decimal. So you can divide it out and get about 0.1171. Okay. What is the probability it is delayed and made by Alaska Airlines? Okay. So we look at the table and we find the number that are delayed and made by Alaska Airlines. That's 501. And out of the total number of flights, which is the same denominator that we had on Part A. Okay, so delayed and Alaska Airlines, there's 501 of these flights out of the 11,000 flights that are delayed and made by Alaska Airlines, which works out to be about 5%, 0.0455. And then Part C, a big difference here, we're given that it's made by Alaska Airlines. That essentially wipes out half the table. If we're going to randomly select one and we know it's made by Alaska Airlines, we can ignore America West, eliminate those two columns, and we now have a smaller sample space. Now we just look at the columns for Alaska Airlines and find what's the probability that it's delayed, given that we're looking at Alaska Airlines. Well, that's going to be 501, the number that were delayed by Alaska Airlines, divided by the sum of the two numbers at the bottom there, the delayed and the on time added together for Alaska Airlines. So given that we're working with Alaska Airlines, there were 501 out of 3,777 flights that were delayed, which is about 0.1327. So I'll say it one more time. Conditional probabilities, usually, I didn't use the formula from the previous slide. Usually you can compute conditional probabilities more directly from the information. Okay, you're restricting the sample space.